I'm going to show an area proof of the Pythagorean theorem. And so what we're going to do is we're going to create 3 copies of this triangle ABC and then look at the color coding, right? The blue, the green, and the red. Because when we create them, we're going to stack them side by side. Let me just show you, right? So you see when the animation happens, I can put B up here, and then I can put A here, and then I can put C here, and this will be a right angle. That's what we're trying to accomplish. And here you go. There the triangles are folding out. But what's important is if you follow the color coding, you can see 4 copies of triangle ABC. And so all the green segments have the same length. They're B. And all of the blue segments have the same length. They're A. And so notice now that we have a square and the side lengths are A plus B, right? I have the blue A and the green B on every side. And I won't continue this. Well, I guess I will, at least to there, right? So I have A plus B, that's my square, the side length of my square. So of course, I know that the area is the quantity A plus B is, the area is equal to A plus B quantity squared. Okay. So I also can just look at these squares, right? I have, 1, 2, 3, 4 copies of this triangle. And so I can just calculate its area, right? Which is, since it's a right triangle, then either A or B could be the altitude and the other can be the base. So 1/2 the base times the height. I have 4 of them, so multiply by 4. And then what I have left over in the middle is this c squared square. Okay, so that's where we get this equation, that c squared, that the area of that of the whole square, of the big square, is equal to c squared plus 2ab. And now I hope you can see where we're going with this. We're going to use the algebraic properties of real numbers, which means we're allowed to do normal equation solving things, right? We know those areas are equal. They're the area of the same figure. And then I'm going to expand the left, right? So I just multiplied out. And now they both have this 2ab on both sides. So when I subtract 2ab from both sides, I just get a squared plus b squared equals c squared. So this is a really visual proof. This is probably more the way the Greeks thought of it, as more than the other proof. The other proof is a similarity proof where we use, it turns out that there's a way to create similar right triangles inside every right triangle. And the similarity proof is far more algebraic and much less visual. And that's fine, but the Greeks probably did it this way. And then you can also see why we don't, why it's equivalent to the Euclidean parallel condition. Remember, we did not have rectangles in neutral geometry. And as soon as a rectangle exists, then we have, then we know we're in a Euclidean geometry. Well, this you can see requires very much having the ability to take these triangles and line them up and have these perpendiculars lead to, that these are parallel, the vertical lines are parallel and the horizontal lines are parallel. To be able to get all of that, we need to have rectangles that actually exist. So the Pythagorean theorem is equivalent to the idea that these triangles will in fact turn into a rectangle, particular kind of rectangle, in this case a square, but that's why the Pythagorean theorem is equivalent to the to the Euclidean parallel condition, which means if the Pythagorean theorem works for every right triangle in the geometry, then the geometry is Euclidean. And if I have a Euclidean geometry, I know the Pythagorean theorem works for every right triangle in the geometry.